Morning, everyone. Morning, Hike. Morning, Azra. Morning, Nikolai. Morning, Downey. Morning, Charlie. Morning, Ava. Morning, Ryan. Nikolai, you think you're first? These guys are pretty quick. I'm not sure who Snazzy Dog is. Why did the star get arrested? Nice. It was a shooting star. Nice. Hi, Miles. Wearing the same sweatshirt. Like it, Downey. Alright. Agenda today. Doing DNA number 6. It is the last DNA on the sheet. May 13th. So we do have a quiz tomorrow. It is an XL. It is going to be worth twice as much as a normal DNAC because there will be twice as many questions. There will be 12. It'll be in 2 parts. 6 questions from last week, 6 questions for this week. And just as a little side note, I am not a fan of the format of 2 weeks because I think it gives too much time in between the first set of questions and the second set of questions. I'm looking for these to be quick assessments for the week. I'm not looking for these to be major tests. So because of the structure for the rest of the weeks that we are in school, where there's pretty much a day off for you guys, and then there's Friday where there's no new work, there's really only 3 instructional days every single week, which you guys like, obviously. But it kind of ruins the flow of my DNAs, so lucky for you, this will be your last DNA. And it'll be your last DNAC. Unless I can figure out something a little better. I think there's just too much time between DNA number 1 this week and DNA number 6. And there's no point doing a DNA sheet when you only have 3 instructional days during the week. So, you probably like that. I'm not a fan, but I can't think of anything better as of this moment, so we'll just really focus on the assignments. Alright? I mean, some of the assignments might get a little longer. So, DNA number 6 itself. Describe the life cycle of our sun. Think of the stages from the extend section yesterday that you saw and you put in your table from the Star in a Box simulator. And then, will it end its life with a supernova? Or would it also become a black hole? Alright? So, will it be supernova / black hole at the end? Yes or no? So, describe the life cycle, describe the stages it's going to go through, and then, is it going to have that impressive supernova? Or is it going to become something which has such incredible gravity that not even light can escape? After we go over this question, you finish your sheet. I would turn that sheet in right away so you don't forget. Due before midnight. Should be done. Turn that sheet in. And then Seeing Stars is also due before midnight. We'll hopefully finish it today. There's only 3 or 4 evaluate questions. And one of them I already kind of went on about yesterday because I didn't realize Kimmeline was asking me an evaluate question. I thought she was just asking me for a fun question. I forgot I snuck that in there. About nucleosynthesis, aka how do you make elements more than hydrogen? So, DNA number 6, life cycle of our sun. Star in a box, on normal, open the lid, different masses. You can go to 0.2 up to 40 times the mass of our sun. I'm at 1 right here. Size, temperature, and Kelvin. Kelvin is based on absolute zero. So 0 Kelvin is absolute zero from last year. There is no movement. There is no thermal energy. You cannot have negative Kelvin. For Celsius, it's like negative 300 some degrees Celsius. Brightness, the amount of time it was in a certain stage of its life, not in order, but just the amount of time. And then the mass. And remember, mass can change depending on the volume, or I should say, the density can change depending on the volume. So, let's go normal, we'll hit play. Currently, we are in a main sequence. That means we are in the adult life of a star, alright, or the teenager side of a star, moving into older period of life, the red giant. We have finished up hydrogen fusion. We're now starting to fuse helium together. That produces more energy, and it's going to cause the star to expand. So right here, fusion is winning the battle against gravity, and it's starting to expand. It's not blowing apart. This is a very slow process until gravity can stabilize it. Right about there. Right? So it's at a red giant. So we went from a main sequence to a red giant. You're following that black dot being our sun, our star. It's just showing you the curve that it's going to trace. Alright? Any star in here is considered main sequence. So when the black dot is in this line, it's a main sequence star. So that means it's going to pass back through that area. It's going to happen very, very quickly. So red giant, and then it collapses back down again. Really, really fast. So let's come back here. So this red giant, once helium is done fusing together, there's not enough mass to fuse those more heavier elements further, and so gravity wins and collapses the star down into something that we can't even see, a white dwarf. So essentially collapses all the material down into its core, and we get a white dwarf. So there are 3 phases there: main sequence, red giant, white dwarf. Not all stars will have that same effect. Alright, so again, we're doing 1 through 6. So DNA number 6, what are the stages? What is the sequence for our star? Our sun is a yellow main sequence star that will progress to a red giant start fusing helium now and expand against gravity. And then lose its outer layers and gravity will collapse it into a white dwarf. this whole thing will happen in about 5 to 6 billion years. And I'm not cutting anything off. It just says A right next to the camera. Alright, so our sun's a yellow main sequence star that will progress to a red giant, start fusing helium, then lose its outer layers. Gravity will collapse it into a white dwarf. So, sun now. Sun after. Sun at the end of its life. Okay? That red giant would actually be even bigger. Will this make the Earth have a lack of thermal energy? Well, here's the thing, Logan. It's not going to be so much a lack, it's going to be a massive increase of thermal energy. Astronomers are still unsure, but it was originally thought that because when the sun expands to a red giant, it's going to expand to about the size of the distance from the sun to the Earth now. So it's going to expand to about 1 AU in diameter. It would absorb the Earth, destroy it, vaporize it, however you want to look at it. Or, as it's expanding, it might actually, through solar wind, push the Earth away. But at the same time, the amount of radiation it's going to receive is going to be extraordinary. So either way, it'll be incredible amounts of thermal energy to the point where life on the surface probably won't exist, or the Earth itself won't exist anymore. So yeah. Are white dwarfs brighter than those main sequence stars because they're all collapsed down? Well, we can actually take a look. Brightness. Brightness ends a little dimmer than where we start as a main sequence star. Good question. Are those white dwarfs brighter? Because they must be, if they're more dense, then they must have the same amount of energy, just in a smaller amount. So we start here, right? I'll go fast. So 1.3, 11. As you get bigger, obviously you get much brighter. But you're not getting much hotter. And then you stay bright, and then you drop in brightness. So it's a dramatic drop in brightness when you become a white dwarf. Do white dwarfs have as much gravity as neutron stars? So we haven't really discussed neutron stars. We'll do that today. But a neutron star is the core, like a white dwarf would be for a small main sequence star. A neutron star would be the equivalent for a very, very large, massive star. All right. White dwarfs do not have as much gravity, nor do they have as much energy as a neutron star, because they don't have as much mass. All right. And as we've kind of learned a little bit, is mass is going to affect gravity. More mass, more gravitational attraction, more gravitational energy. So you need high amounts of mass to create really extreme kinds of things. And that leads into what I was going to talk about next, Hike, is this right here. Will the sun end its life as a supernova or a black hole? And obviously from Star in a Box, no, it ends as a white dwarf, right? But there are obviously stars that end as neutron stars, supernovas, or black holes. You just need greater mass. So what's that limit is what I wanted to ask you yesterday, because it was going to help you today. So just quickly coming back here before I jump off. Oops, why is that so thin? There we go. Not enough mass to go supernova. It's a stellar explosion. And that also means and be a black hole or a neutron star. So before I kind of get into talking about the mass you need for a black hole neutron star, just establish that the sun itself will not go supernova at the end of its life, and it will not be a black hole or a neutron star. I should rephrase that. There. In neutron stars, I'm pretty sure there is a weird type of matter that can really mess up planets and stars around it. In their cores, there's a theoretical matter that is the most dangerous stuff in the universe. So Hayden's kind of talking about there is something called strange matter. Hypothetically, there is something called strange matter, or strangelets, that if they touch matter, they convert matter into strangelets. And so it's kind of like a gray goo problem, that if you have a strangelet somewhere in the universe, it'll collide with other matter and then convert other matter into strangelets, which do not follow the same rules as our typical baryonic matter that we're made of right now. So it's theorized, Hayden. As of right now, no one's seen any, so that's a good thing. Yeah, it's called strangelet if you want to look that up. Can you show one star that becomes a supernova? That's exactly what I'm going to do. Just make the mass really high. Just crank it up. So, well, we got to find out what the limit is, right? Because just because it goes supernova doesn't make it a black hole. Just because it goes supernova doesn't mean it becomes a neutron star. So, 2 solar masses. We're going to run these as the fastest. So a little trial and error. It's obviously going to follow the same curve. It just takes a little longer, and it goes through multiple giant phases. But it goes red giant down to white dwarf. So this curve is for the sun. So if it has that kind of like slingshot, the boomerang shape, then it's just going to be our sun. Alright? Still kind of a boomerang shape. A very, very low brightness white dwarf. But it may actually become blue instead of a red giant. 6th. See if it kind of goes the same way, because this is pretty extreme right here. Red giant, white dwarf. Nope, still follows that curve. This will be interesting. Red giant, multiple stages, supernova imminent, explodes, casts off all outer layers, and the core gets crushed down into an intensely dense state. So one other thing that we can kind of talk about, Hayden, is that there could be strange matter in neutron stars because it's so incredibly dense. But the reason why they're called neutron stars is because the matter that a neutron star is made out of is pretty much all neutron. Because the gravity and the density is so intense that the protons and the electrons get squeezed together, and they make neutrons. So all the particles in a neutron star are neutrons. So it's incredibly dense, incredibly energetic. Can no longer undergo fusion. There's iron in the core. Blows apart. Leaves behind the core in an intensely dense state. So we get a neutron star, we get a supernova and a neutron star at any mass of 10 or greater. So 10 solar masses or greater, you'll get a supernova and a neutron star. Okay? 20, you're going to get a supernova. Again, see that disconnect? I mean supernova. And we end as a neutron star. Where are we going to get that black hole? Black hole. At 30 solar masses, you'll eventually have enough gravity that you'll even collapse the neutrons in a neutron star into a point, a single point, like a graph, that is infinitely dense. So that means its volume basically doesn't exist, and it has all its mass in that one spot, that one point. So you create something called, Einstein would describe it as a singularity, where density approaches infinity, which means the escape velocity, so the speed something needs to move to get away from something due to gravity, is stronger, is faster than the speed of light. Because nothing goes faster than the speed of light, the black hole doesn't emit light. Anything that falls into the black hole's gravitational field stays in that gravitational field. If it crosses what we call the event horizon, it's like the edge of a waterfall. You never go back up. All right. Does that mean all black holes are neutron stars at some point? Maybe for fractions of a second, Hike. It's a good question. I don't have a 100% answer on it, but I would assume that for maybe a fraction of a second, it would be what we would call a neutron star, but then collapse down. There's a second way to get a black hole. You just need a lot of mass, right? Have two neutron stars collide together. That will have enough mass, enough energy to put all that dense matter in one singular spot to create a singularity, to create a black hole. So LIGO saw that. LIGO measures gravity waves in space. As they pass through the Earth, you can measure and look at the direction it came from and see that a black hole and other objects are in that location. So if you have two neutron stars merged together, you can get a black hole. These are stellar black holes. That means they're small. But there's something called supermassive black holes that are the center of galaxies. And those supermassive black holes may have helped galaxies form. We just kind of ran out of time. I had a whole assignment about galaxies, but we have to get at least some Earth stuff in before the year is over. So we're going to do some gravity after seeing stars, and then we're going to talk about the Earth, the layers of the Earth, and density of the Earth. All right? So I want to move on. If you have other questions, ask them. We'll come back to them later. And the reason why I kind of went off on a tangent is because in seeing stars, I'm asking you a pretty general question. What happens to all types of stars throughout their lives? So even stars not like our sun, what's going to happen to them? All right? So I kind of explained number 6 already yesterday, and it was just based on the idea that we are fusing elements in the cores of stars. So how do elements beyond hydrogen exist in our universe? Here's ptable.com, great website. I actually had an old student email me. He's a junior. He had questions in chemistry. I told him to go to ptable.com like we used to do and go through some of the more advanced information like electronegatividity to talk about how bonding works. So always remember ptable.com. It's going to help you in the future. All right. Here's hydrogen, atomic number 1, 1 proton. How do you get the others? Because hydrogen was the first element after the Big Bang. Okay, energy becoming particles, particles forming atoms. Hydrogen is the easiest one to do. It's 1 proton and 1 electron. So how do you get the others? Well, like I said a couple days ago, we take hydrogen, we fuse it together. 1 plus 1 equals 2. Okay? You start fusing helium and hydrogen now, you can start to get lithium and beryllium, 3 and 4. Alright? Fuse 2 beryllium atoms together, 4 plus 4 is 8. Now you get oxygen. Alright? or fuse helium with beryllium, you get carbon or carbon. Boron, nitrogen, fluorine, neon, magnesium, phosphorus, sulfur, chlorine, argon, potassium, calcium. You can get all these elements in the cores of stars up until iron. So from 1 to 26. Atomic numbers 1 through 26 can be fused for energy in a star's core. Okay? This ends with iron because there is not enough gravitational pressure to fuse iron atoms. So iron, not enough energy, it's going to kind of repel and refuse to fuse any further. So you hear some astronomers refer to as iron being like poison in the core of a star. Once iron starts building up inside the core of a star, that sun is, or the star is doomed, all right, to go supernova, so on and so forth, all right. So how do you get those other elements? How do you get 27 to 54? How do you get 27 to xenon? How do you get from cobalt down to xenon? Well, when stars explode, like I kind of said yesterday, the pressure wave that comes away from a supernova is so incredibly strong that you're going to fuse those atoms as they blow off from the star. So supernovas are the most powerful explosions in the universe. And in that explosion, you're going to have so much energy released, more than the gravitational pressure of a star, that you can fuse those larger elements together. Okay? So the first several rows can be made inside stars by regular fusion. The next set of rows in the periodic table have to be made by fusion, but through a supernova explosion. So we're talking stars incredibly more massive than our sun, 10 times more massive, right, from this. 10 makes that break in the line, which means supernova. And then to go on, to finish the periodic table, to do rows 6 and 7, you need something even more powerful, more pressure than a supernova. I mean, they're one of the most largest explosions in the universe. How can you get something stronger? Well, black holes coming together, well, they have so much gravity you can't really release anything. But if you have two neutron stars collide together, yeah, it's going to make a black hole, but there's not all the mass is going to go into the black hole. So, rows 6 and 7 are made by neutron stars colliding together. What is a neutron star again? It is the end result. It is the core of a star 10 times more massive than our sun. It is the core left over from a supernova. So it transitions, starts fusing again. It's going to start blowing up. Boom. And now it's a neutron star down here. So neutron stars are the cores of stars much more massive than our sun. If you take two of those cores and you smash them together through gravity, with the collision itself, you'll generate enough energy to fuse together atoms and get platinum and gold. So if you got gold on right now, it came from two neutron stars colliding together billions upon billions of years ago. That explosion seeded the nebula that would eventually allow our sun to be born from. So as my friend Carl Sagan used to say, we are made of star stuff. sagging, as Mr. Sanford would say. Or Manfredo, I'm sorry. Now kind of like moving on. That was from yesterday a little bit. 7. What happens to all types of stars throughout their lives? So kind of describe, our sun is going to go yellow main sequence, red giant, white dwarf, but not all stars are going to go that way. 8 is from today's DNA, right? Stellar phases. Take a look here. So, from the Chandra Observatory, which is operated by Harvard, but done through NASA. All stars are going to start very similar. They're going to be collapsing gas in a cloud. Who is Mr. R.I.? Oh God, because you sign up as Mr. R.I. and remind, no idea who you are. All right. So more mass means you're going to be bigger and you're going to be hotter, right? Blue is hotter than red. So if there's not enough mass, a star stays as a brown dwarf, and that's like the boundary between a star and a planet. It's like a gas giant that is big enough to be bigger than Jupiter, but not large enough to undergo fusion at the core. So brown dwarfs are brown because they don't have fusion. All right. Red dwarf, they stay red dwarfs and then eventually become a white dwarf. These stars will last a very, very long time. We're talking billions upon billions of years. Red dwarfs last a very long time. Because they don't have a lot of mass, they use up their hydrogen very slowly. Gravity isn't as strong. Okay? For the sun-like stars, we go yellow main sequence, red giant, blow off the outer layers, become a white dwarf. Okay? Some white dwarfs can explode. We don't have to get that in detail. But if a white dwarf is able to siphon off energy from a binary star, a binary partner, that star could go supernova with the extra energy. But we're not going to talk about that. All right? Yellow main sequence, red giant, white dwarf. Okay? That's our sun right there. Other stars, you start getting into larger masses, 10, 20 times the mass. All right? You're going to go blue giant, red giant, blue giant, explode, neutron star. Okay? Once you start getting into the higher masses, these blue giants are going to go supernova and leave back a black hole. Black holes have gravity stronger than the speed of light. Nothing will escape it if it passes the event horizon. So with the greater mass means a brighter and hotter star, but these stars last a lot less time than our sun or a red dwarf, because the bigger you are, the more hydrogen you use up faster. Okay? So this picture kind of describes the progress of time left to right. Obviously, you're focusing on this line right here. You're focusing on neutron stars and then the black holes. Alright? They all will expand because they undergo fusion of heavier elements as they age, Hayden. Yeah. But these expand faster or blow up and end their life faster because they use up their elements, especially hydrogen, faster. Right? The bigger the campfire, the more wood you need to keep that fire going, right? So they use up their fuel faster. They use up their hydrogen faster. You have a small campfire, you can let that thing burn for a while. Those embers, those coals will burn for a while. That's what a red dwarf is. It just keeps burning. Never really expanding because it's using its hydrogen very, very, very efficiently. And it doesn't have enough pressure to fuse the helium to really expand into a red giant. So hopefully you've been working in the evaluate questions. As you have questions, throw them up like Hayden and Downey just did right now, and I'll address them as you work, but your focus is on finishing this evaluate section, which should take you right there to the end of seeing stars. So seeing stars and your DNA sheet are due today before midnight. If you've been following the timeline that I've been giving you, just doing what I ask you to do each day, one DNA, a section a day, then it's just another day of work. You should be fine. Just turn it in before midnight. Alright? That's fine. So both of these are due before midnight. Just emphasizing that. What's a planetary nebula? We don't have to get that in depth, Downey, but a planetary nebula would be the outer layers of a red giant being ejected as fusion kind of comes to the end of the star's life. So the outer layers of the red giant are ejected off. Fusion is done. Gravity is going to contract the core down. Think of it as not enough gravity to hold the star together, and now it just kind of blows apart as fusion ends. It's not a supernova. It's like a very, very weak supernova. So for number 7, I would just kind of think about what happens to all types of stars throughout their lives. All stars, obvious, all stars start as collapsing gas in space. Depending on their mass, they will be a red dwarf, low amount of mass, or a yellow main sequence, medium amount of mass, or a blue supergiant, high amount of mass. So there's a low, medium, and high. They all start off as collapsing gas, but if there's more gas, if there's more mass collapsing down together, then it's going to be a blue supergiant. If it's just a little bit of pocket of gas collapsing down, it's going to be a red dwarf. Or if there's a yellow main sequence, it's just in between a blue supergiant and a red dwarf. So they all start as collapsing gas. Low, medium, or high is their starting point, right? And then just describe what happens to a red dwarf, describe what happens to a yellow main sequence, and then describe what happens to a blue supergiant. Red dwarfs are going to stay red dwarfs until the end of their life, and they end as a white dwarf. They fuse hydrogen very, very slowly, and there's not a lot of hydrogen to begin with. Alright? Our sun-like star, yellow main sequence, will fuse helium to become a red giant, and then eventually lose its outer layers, become a white dwarf. Blue supergiants can do one of two things. Lower blue supergiants will explode in a supernova, become a neutron star, which is just the core that's left over. And then larger blue supergiants, about 40-30 times the mass of our sun, will explode in a supernova and leave behind a black hole. The core neutron star is going to kind of collapse in and of itself. All the matter from the supernova and the neutron star come together, fuse into an infinitely dense point in space. We call that a singularity. And then the ring around the singularity where light can't escape, the event horizon, we call those together a black hole. And they're not like Pac-Man. They don't wander the universe, gobbling things up. They just have gravity that's so strong, no matter what, you'll never be able to leave, because nothing goes faster than light. And their gravitational force is stronger than the speed of light. So that's another, hopefully, good starting point for you to take on number 7 if you needed it. Again, this is not just the only answer. This is not the only answer. There's more information to include. All right? Number 6, I talked about supernova explosions and neutron stars merging together as additional information. I just talked about how you have the red giant phase, and you have white dwarfs, and you have supernovas, and you have neutron stars, and you have black holes that each branches off from different types of stars. And then use your DNA from today to answer this question. Is going to become a white dwarf. There will be no supernova or black hole because there's not enough mass. Okay? A protostar from Rainey is just the birth of a star. So it has an accretion disk around it, and it's about to start fusion. This is technically called a T Tauri star. Hayden kind of inspired the video of what would happen if the gas giants collided. So, where is it? Oh, it's way back. Ask Mr. G. Colliding the gas giants. This video goes in depth on how you could get the gas giants to form a star. But this is kind of what you're interested in, Rainey. The accretion disk of a protostar, a star just beginning to form. It's the similar way that a planet's going to form. This is matter, dust, rock, gas, all kind of swirling into a central spherical mass because gravity works in all directions. When there's enough mass, about 0.08 solar masses, you can start fusion. And when you start fusion, you get a baby star called a T Tauri star. This is that curve. It's just a little different. I just kind of showed you the region for each. This is an HR diagram if you're interested. You don't have to go that detail. So what would you see from Earth? You'd see an accretion disk with energy coming out the poles, and that would be a protostar. That would be a T Tauri star. A T Tauri star is a baby star. A protostar is a baby star. T Tauri is its name. Eventually, This accretion disk will all flow into the star, all this radiation will calm down, and it'll be a main sequence or a red dwarf. Or if it's really, really big, a blue supergiant. So, if you want to watch that video, just go to the playlist Ask Mr. G. Alright, Nikolai. Catch you later. See you, Ryan. Bye, Hike. Bye, Azra. Bye, Ava. Thanks for coming. So they either become a supernova or a black hole or a white dwarf. Pretty much the end for all stars, yes. That would be the end state. But I mean, you're just kind of like glossing over. Like, they don't become a supernova. I'm sorry, let me rephrase that. So some of them go supernova. They all will either be a white dwarf, a neutron star, or a black hole. Most will be some version of a white dwarf. A little smaller portion will be neutron stars, and very rare will be a black hole. Any other questions? I think most people are good. They've kind of moved on. If you still have questions, send them by email, send them through Remind. I'll get back to you. Before the midnight deadline. Don't forget that. At the end of its cycle, it will die. It's gonna change its color? End of its cycle, it'll die? What do you mean? They stay as white dwarfs or neutron stars until no fusion or radiation is given off anymore. They become just not black holes, but just black balls, or they explode. Yeah. But they will stay white dwarfs and neutron stars for trillions of years. Black holes will probably absorb them before they burn out. And then you only have black holes. And then black holes themselves evaporate radiation through Hawking radiation. and then they explode when they finally evaporate, so that there will be nothing left in the universe. All energy will be evenly distributed. The universe will have achieved perfect equilibrium. But that is trillions upon trillions upon trillions, unfathomable amount of years. Maybe a universe starts through quantum fluctuation. We don't know. Probably never will know. Alright. If you guys are still watching, have a good Wednesday. Tomorrow we will review and take your DNAC.